response 5. Let f and g be the functions given here for all x greater than 0. So it's worth noting we're only looking at x values greater than 0. Part A, find the absolute maximum value of g on the open interval from 0 to infinity if the maximum exists. Find the absolute minimum value of g on that same open interval from 0 to infinity if the minimum exists. Justify your answers. Okay, so if I'm asked to find extrema, right, so anytime you're asked to find extrema of g, that's going to mean that you need to find critical points, right? You need to find critical points, which are going to be when g prime is 0, g prime does not exist, or at any endpoints, right? So included endpoints should show up on my sign chart too, right? So before I can do anything else, I need a g prime, right? And g is going to involve the quotient rule because I have a high function and a low function, right? I'm dividing. So I'm going to go ahead and find g prime first. And it's very likely the AP is giving you credit for the action of finding g prime, especially one that involves the quotient rule is kind of complicated. So low, d high would be a 4, minus high, which is a 4x. D low would be an 8x. Draw the line, square the low, 1 plus 4x squared, quantity squared. Cool. So when I clean up the top, I get a 4 plus a 16x squared minus a 32x squared. So I'm pretty sure I get a 4 minus a 16x squared when I clean everything up, right? And on the bottom, I still have this 1 plus 4x squared quantity squared. If I factor a 4 out of the top, right, which I probably would because it seems easy enough to do so, I'd get a 1 minus a 4x squared over this 1 plus 4x squared all squared. So the thing about the top is a difference of squares. You don't have to spot that if you don't want, but it's helpful to spot that the top has a 1 minus 2x and a 1 plus 2x. So I would probably, and you don't have to, but I would probably rewrite my g prime of x as a 4 times a 1 minus a 2x times a 1 plus a 2x. And then one thing to notice about this bottom number, this denominator is always going to be positive. The smallest that a 1 plus 4x squared could ever get is a 1, because the smallest a squared term could be is 0, right? If you square a negative, it's positive. So the smallest that this denominator could ever be is a 1 squared. 1 is a positive number, so that's basically not going to factor. So a couple things are happening now, right? So I have this as my g prime, right? I'm going to find where g prime is 0. Well, g prime equals 0 when 4, or 1 minus 2x, or 1 plus 2x is 0, right? Well, that's going to be when either 4 is 0, which is a lie, because the number 4 is not the number 0, or when, if you set 1 minus 2x equal to 0, you end up getting that x is 1/2, right? When if you set 1 plus 2x equals 0, you get x is negative 1/2, right? Which won't end up mattering in this window because we were told x is strictly greater than 0, but we'll deal with that in a sec. And there's no places where g prime does not exist because the denominator is never 0, right? So 1 plus 4x squared is not 0 for real numbers. It's not going to happen. The only way that that comes out to be 0 is if you use i's, and we don't have imaginary numbers here. So there are no critical points there. So essentially, I have 2 critical points, but in the window they gave me where x is greater than 0, I only end up with 1 critical point. So I can determine if that critical point is a max or a min, but that's going to be the only one, right? So like there's not any other critical points on this graph. There is an endpoint, but it's not an included endpoint because the graph starts after 0, so that can't be a max or a min. So now I'm going to make a sign chart. And again, how complicated you make the sign chart kind of depends on you. I'm going to go ahead and list all the factors. 1 minus 2x, 1 plus 2x, and then this denominator, which isn't really relevant to me because it's always positive anyway, but sometimes you have a denominator that's always negative, and that could be an issue. So if we put the only critical number I have on here, going up to infinity, right, here's what I know. The denominator is always positive. We talked about that already. A 4 is always positive. 1 minus 2x is a line with a negative slope. So if it's 0 here, it's positive before it hits that 0 and negative after. 1 plus 2x is a line with a positive slope, so it's 0 at negative 1/2, which doesn't even show up on this graph, and is positive for anything after negative 1/2. Again, if you don't like that option, you could just pick a number between 0 and 1/2 to plug in and test these things, but I assure you that that's not super fun. So I end up getting that my g prime is positive and then negative. What that means is that my g is going up, leveling out, and going down. So that means that g of 1/2 is a max. So, and they specifically asked me to find the actual value at that time, so we'll go ahead and do that. So there is an absolute max at g of 1/2, right? That's the absolute max. So if I plug a half in here, that's going to, when I plug into the original g, that's going to be 4 times a half, which is a 2, right? Over a 1 plus a 4 times a half squared is a 4th. So I get 2 over 2, which means that the absolute max is 1. So the absolute max is g of 1/2, which is 1. There is no minimum value, right? Because we can see that this thing doesn't reach a min. So there is no absolute min on this window. Now there is a horizontal asymptote, so we'll talk about that at some point. There's a horizontal asymptote at y equals 0. If it comes up, we can talk about that. Cool, and justify my answers. This is plenty of justification. Justify doesn't necessarily mean a sentence with words. You can justify it by clearly labeling your sign chart for g prime and g. That's fine. If you want to justify it with words, you could say that g prime switched from positive to negative at 1/2, right? And that's what makes it a max. All right, part B. Find the area of the unbounded region, right there, that's why this is a BC question, in the first quadrant to the right of the vertical line x equals 1, below the graph of f and above the graph of g. So what they're saying is, here's the line where x is 1, right? We know that the f function has a vertical asymptote when x equals 0, right? You can see if you plug a 0 in that denominator. And because the numerator degree is smaller than the denominator degree, not only does it have a vertical asymptote at 0, but it has a horizontal asymptote at y equals 0. So essentially, f looks something like this forever, right? It's got a horizontal asymptote. So it's my f graph, right? And there's f has a horizontal asymptote of y equals 0, right? But my g graph, right? G of 0 is actually 0, and we know that g maxes out at, if I put this 1 here, we know that g of 1/2 is 1, and that's its max. And then it's going to go down forever. But the trick is that, again, this numerator degree is 1 smaller than the denominator degree. So this guy also has a horizontal asymptote of y is 0. So he's also going to approach this way. He also has a horizontal asymptote of y equals 0. So the area that they're talking about is starting at the vertical line of 1 and then going this way forever, right? But as you can see, those two graphs eventually are approaching the same point, even though technically they're not the same graph. At some point, as we go to infinity, they are approaching, both of them are approaching y equals 0. So what we need to do is we need to integrate from 1 to infinity of this f minus g, right? So essentially what we want to do, and I might end up erasing this graph to buy myself some space, but you get the gist. So what we want to find is the integral from 1 to infinity of f of x, which is the top curve, minus g of x. Now, you probably could have figured this out without actually drawing it, but I thought giving you a visual would help you understand how it's working. We're not supposed to have infinite bounds, so what we're going to do is we're going to call this top bound b, and we're going to say we want the limit as b approaches infinity of the integral from 1 to b of f of x, which is that 1 over x, minus g of x, which is the 4x over 1 plus 4x squared with respect to x. So I basically have to do the antiderivative for both of these. This guy's a simple natural log. This guy's going to be u sub. How much you need to split these apart to do the integral is kind of up to you. So I'm going to erase this graph now and buy myself some more space to do this. I feel comfortable, like me personally, a person who has done a lot of calculus for the last 20 years, integrating this in my head without doing u sub. That's great for me. If that's not something you feel comfortable with, you might have to do a little more work. So if you need to do it, you can split this into two separate integrals, right? The limit as b approaches infinity of the integral from 1 to b of 1 over x dx, which is just going to be a natural log, minus the limit as b approaches infinity of the integral from 1 to b of this 4x over 1 plus 4x squared. Now, again, I don't feel like I personally need u substitution to work through this, but if you feel like you do, then you by all means should. If I were doing u substitution with this, right, if I just did the work on this integral only, my u would be the denominator, 1 plus 4x squared, and my du would be an 8x dx, which is conveniently a multiple of what's already the numerator, right? So I basically get a du over 8x is my dx, and this integral would turn into a u on the bottom, and then a 4x dx would cancel, sorry, don't mean the dx, 4x, would cancel with the 8x, leaving me with a 1/2. So this essentially would be an integral of a 1/2 du over u, which is just another natural log, right? So basically what happens is I get that this is the natural log of the absolute value of x, evaluated from 1 to b, and again, that's a limit as b approaches infinity, right? Minus, and actually I could, since I now know that this is just going to be a 1/2 the natural log, minus a 1/2 the natural log of the thing that would have been u, which is the 1 plus 4x squared. Again, that whole thing can be evaluated from 1 to b, right? So this is the limit as b approaches infinity. If I use some log properties, a couple things are going to happen, right? I would suggest that you bring this up, and then that you use this subtraction to make this an x on top of that quantity. So I can make this the natural log of an x on top of a square root of 1 plus 4x squared, evaluated from 1 to b, right? So when I go ahead and plug those values in, I'm going to get that this is the limit as b approaches infinity of the natural log of b over root 1 plus 4b squared, right? Minus the natural log of a 1 over the square root of 5, right? Well, the thing about this is there's a couple ways to get here, right? One option, if you want, is to go ahead and combine these now into a single statement, which is fine, right? Another way to deal with this is to recognize that these two degrees are actually secretly the same. Because although this is a b to the first on the top, this is a b squared inside a square root, which means it's netting a b to the first. So essentially what's happening here, right, is that this thing is fundamentally, as b goes to infinity, behaving like the fraction of the leading coefficients, right? So what that's going to look like, right, as we go to infinity, is that this is going to end up behaving, for all intents and purposes, essentially like a root 4 on the bottom, right? Like a 2, right? So this is going to behave like a natural log of a 1/2 minus a natural log of a 1 over root 5, right? Now, you can combine that, or you can leave it sort of as it is. If you combine them, it would be this quantity divided by this quantity. So if you combine them, you'd get the natural log of a 1/2 divided by a 1 over root 5, right? Which is the same as the natural log of a root 5 over 2. Now, that's the answer that I would have landed with, and you don't actually need the absolute value at that point because they're both positive quantities. You could have dropped the absolute value somewhere in here. The AP went with a slightly different answer, which is also fine, right? The AP, at some point, left that as a root 4. In fact, so they left it as a root 4, which meant that they got that it was the natural log of the square root of the quantity 5/4, and then instead of treating it as a square root, they put it as a 1/2 exponent, which they dropped down in front. So the AP's equivalent answer was 1/2 natural log of 5/4, and there's nothing wrong with that, right? So it depends on how you simplify what answer you get, but whichever way you go, right? Now, so if you had chosen earlier on to maybe simplify a little bit less, you may have gotten a simpler answer. You could have also combined the terms here and figured out essentially that you would have gotten a root 5 over a root 4, which is how they got here. There's different ways to get there, but that's really what they were looking for. So you needed to make sure you had the integral, you needed to do the anti-differentiation correctly, and then you needed an answer.